We're going to be talking about local linearization. And the good news is that everything that we do today, we've actually already done. But we're going to put new names and a new use to it. Specifically, the local linearization of a function is simply going to be the tangent line. So let's consider. We have a function f of x, and we have a point C. We're now going to construct the tangent line, the line tangent to the graph of f, at x equals point C, kind of like so. And we ask, what is the equation of the tangent line? At x equals C. And we have a nice format for doing that equation. We need a slope, and we need a point. And how are we going to spell the slope of the tangent line at x equals C? F prime of C. Yes. So we need to make a careful distinction between f prime of x, which is the slope of the tangent at a point x, and f prime of c, which is the slope of the tangent at the specific point C. So this slope right here, because we are tied to the x value c, the slope is not f prime of x, but f prime of c. You see the distinction. Likewise, what is our point here? C. Exactly. And now, armed with these two pieces of information, we can easily construct our tangent line. Y minus y1 equals slope times x minus x1. And this is a perfectly good way to write it, but for our purposes today, we're going to add f of c to both sides to get y as a function of x. And this we are going to describe, it is the equation for the tangent line. We are also going to describe it as the local linearization of f of x at x equals c. The local linearization of f of x at x equals c.
Y equals something.
Yeah, that's how we appreciate
Y equals something.
Or the tangent line, she changes that y minus f of c.
Well, I'm going to put it in this form, and you'll see why, because we're going to use this in just a minute. So if I asked you just what is the equation of the tangent line, this would be a perfectly acceptable answer. But our local linearization, we're going to specifically write it in this form. And by putting it in this form, I'm actually doing a couple things. One is I'm going to make it useful for us. And the second is I'm setting you up for something that you're going to do in Calc 2 later on. Now let's go through and understand what the words mean. This English suffix, ization, means essentially to make something like. So if we colorize a photo, that means we take a black and white photo and we add color to it. So we make it like a color photo, essentially. Here, linearization means that we're going to take a function that is clearly not a line, f of x is clearly not a line, and we are going to pretend that it is a straight line. Now, our pretense is only going to work for x's that are close to c, and that's the purpose of the word local. By saying that I have a local linearization, this means I'm going to make f of x be like a straight line, but only for x's that are local to c, that are in the locality that are close to c. And our linearization is at a specific point x equals c. It is only valid for x's close to that c. So here is the theorem that goes with our local linearization, and I will not prove it at this time, but we're going to see this again later. And our theorem is this. For x close to c, the value of f of x will be approximately equal to the value of the local linearization. In other words, for x is close to c, I can pretend that my function is a straight line and only lose a little bit of information that way. Now let's come back and see it in the graph, because it's really easy and beautiful to see it in the graph. Everybody take a look at the tangent line, which I'm going to turn a different color here to make it, pick a color.
Purple.
Purple. Tangent line's purple. There. That's like purple gray. Okay, fine.
Yellow.
Woo! There. Yellow. I like that. Okay. So there's our tangent line. Now here's the thing. For x's that are close to c, notice that visually I can hardly tell the difference between the black f of x and the yellow tangent line. That visual representation is saying exactly what we say here. For x close to c, f of x is very close to the local linearization. Now come back and look at x's that are far away from c, like over here. Notice that for this x, way over here, my curve and my line are very far apart. But when I come back over to an x over here, when it's close to c, my curve and my line are practically indistinguishable from each other. They will have very close to the same values. Now, if I zoomed in enough, I would see some difference between them. But I have to zoom in a lot to see that difference. Okay?
So for x close to c also means that x goes to the c to the left and c to the right.
For x's on both sides, yeah, of c. And the closer that x is, the better the approximation is, generally speaking. Okay? We do this kind of thing instinctively all the time. Suppose that Jason's driving along the highway and we're waiting for him to come. We call him up and we say, "Are you going to come?" And he says, "Well, I'm almost there. I'm 5 miles away, but I'm in traffic." And so we ask, "Okay, well, how fast is traffic going?" And he says, "Well, it's only going 30 miles an hour." In other words, 1 mile every 2 minutes, right? So we do a quick computation and say, "Oh, so it'll take you about 10 minutes to get here." Look at what we just did there. We took his current rate of change, 1 mile every 2 minutes, and we pretended that the traffic is going to last at that same rate, going to travel at that same rate for the rest of the time. So 5 miles times 2 minutes per mile would be 10 minutes. We're doing a local linearization. Any time that you assume a constant rate, you are pretending that the function that you're dealing with is a straight line. It's a local linearization. Now, it's a linearization, and it will be local if you're using it for small amounts of time. If he's 200 miles away, and you assume the traffic is going to continue at 30 miles an hour, then you are wishing very, very bad traffic luck on him. Because we would assume if he's 200 miles away, at some point he'd break free from that traffic and he'd start to go fast, right? So a global linearization is not a very good assumption. But a local linearization is pretty good. Does that make sense to everybody? Okay. Now, let's actually see how this works. Jason.
Local means small range.
Exactly. For x close to c. Exactly. Okay. Now, let's do an application of this. Let's let f of x equal the square root of x. And let's consider c equals 4. And first thing I'd like for all of you to do is to construct, that's the math word for create the equation for, the local linearization. For f of x at c equals 4. Go.
No question.
Mm-hmm.
Do you plug C first to find the prime of C, or to find the prime of X and
You have to find f prime of x in order to evaluate f prime of c. Yeah. So you can see that our first step here has to be f of x equals root x, and what is f prime of x?
small ratio?
Right. This does not give us the information that we need yet, but it's about to, because what is f of 4 equal to? And what is f prime of 4 equal to? 1/4. Exactly. And that is the information that we need for the local linearization at c equals 4. And in particular, we can just carry this on. Y is going to be equal to f of 4 plus f prime of 4 times x minus 4, which is 2 plus 4 of x minus 4. Jason, do you mind hitting the door, please? Okay, so that's our local linearization. Now, let's use our local linearization. Here's where it gets magic. Watch this. Consider this question. Estimate the square root of 4.2. Now, if you have a calculator, you can whip out your calculator and say square root of 4.2, blah, 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 and the calculator will give it to you. But let's say you're stuck on a desert island. Or you're at a party and you're trying to impress your friends with your mathematical skills, whatever. For some reason, you want to estimate the square root of 4.2, and you do not have a calculator to give that to you. Your local linearization can give you a very good value without you ever having to use a calculator. I can say that because 4.2 is close to 4, therefore, the value of the square root of 4.2 will be close to the local linearization of f, evaluated at 4.2, which is 2 plus 4 4.2 minus 4. Which is 2.05. Now, for just comparison purposes, let's compare that to the real value of the square root of 4.2, which is approximately, in 4 places, 2.0493. We found it in the other class. How close is our local linearization? Pretty darn close. It's within 0.5%. Less, even. So the virtue of our local linearization is that once I have it, I can now use it to estimate values of f without having to work hard at all. Which is exactly what we did in the traffic case, right? We estimated the amount of time with a simple multiplication we did. Okay? We can recycle this local linearization for as many x's as we want to, as long as we don't get too far away from x equals 4.
What would you say is too far away?
Ah, that's a whole other topic that you really address in numerical analysis class, where you relate the distance between x and c to the amount of error in your approximation. We're just going to kind of wave our hands at this point and just say stay close. Okay? So just for comparison purposes, pick another x that's close to 4. Oh my, okay. Let's check out the square root of 4.0001. And let's say then that this is going to be approximately the same as the local linearization evaluated at 0.000 4.0001. And we can plug it into exactly the same straight line equation. And then simplify. 1/4 of 0.0001 is 0.000025. So that my square root is 2.00002. Wow. Let's see how close we are. Using our calculators, we have, sometimes my calculator doesn't turn on me. Come on, buddy. Do your thing. What you got?
It's the same.
It's the same. Well, how many, what is it, how many places?
1, 2, 3, 6.
Oh my goodness. Wow. Perfect. That's really impressive. It's really impressive, isn't it? And it works also for x's that are to the left. So if I choose maybe 3.9, something like that, then square root of 3.9 is going to be approximately equal to y of 3.9. Notice the use of the approximately equal to. The reason I'm doing that is that I'm recognizing that f is not its local linearization, but is close to it. But then I use an actual equal sign here because I'm actually evaluating local linearization. And observe that because x is to the left of 4, I'm going to get a negative quantity inside here times a positive slope. Means it's going to be 2 minus, let's see, minus 0.1 divided by 4 is 2 minus 0.025, or 1.975. What's the actual square root?
1.9748.
I'll take that. That's really good, isn't it? So the local linearizations are extremely powerful. But if you get too far away, they're no good anymore. So for example, suppose I ask, what is the square root of 8? 8 is not close to 4. All right? But suppose I tried it anyway. Then what I would get is 2 plus 4 of 8 minus 4, which is equal to 3. How does that compare to the real square root of 8?
2.828.
2.828. And you can see that my tangent line is starting to drift away. Worse things can happen. Suppose I ask you, what is the square root of negative 1? Now, already, you know that's a funny question, right? What's the real answer to the square root of negative 1? Answer, it's not a real number, right? So this is does not exist as far as the reals are concerned. Yeah, we could talk imaginary numbers, but as far as the reals are concerned, there isn't one. Then, nevertheless, I can get an answer out of it as 0.75. Well, that's just a lie. This is just wrong. And it's wrong because negative 1 is very, very far away from x equals 4, and I'm getting spurious results right here. So the moral of the story is that these guys right here are not valid uses because the x values are not those to C. And in the last case, because the x value that I pick is actually outside the domain of the function. So observe that our local linearization has a domain of all real numbers, whereas our function does not. So I present these cautionary examples to you just to say, don't abuse it. Yes?
Okay. If x is close to -1.
Ah, good. Then I will not be able to generate an f or an f prime for it, because it will be outside the domain. Excellent question. Does this make sense to everybody? Now, I want to observe how little information we actually need to make this happen. Suppose I tell you that f of 3 is equal to 6, and f prime of 3 is equal to -1, and I ask you to estimate f of 3.1. Something like this. Notice you don't know anything else about f, except two things. The value of f at the point and its slope. Graphically, here's what we've got. 3, 6, and we've got a slope of -1. That's all we've got. But I can use just that information to estimate the value right here by following the tangent line down. We construct the local linearization. I'm going to use LL as the abbreviation for the local linearization. Y equals f of 3 plus f prime of 3 times x minus 3. And that gives us 6 plus -1 times x minus 3. And now I can say that f of 3.1 is, here's our local linearization theorem, which is 6 plus -1 plus 3.1 minus 3, which is 6 minus 0.6, or 5.4. No, right. 6 minus 0.1, which is 5.9. Yeah, that's right. So I can estimate values knowing only two pieces of information: the value of the function at that point and the slope of the tangent line. In other words, where I am and where I am going gets me close to where I need to go. When you get to Calc 2, we're going to extend this idea and include additional information. What happens if I know f double prime is 3 and f triple prime? Then I can incorporate that also into my estimation to make it a better estimate. So that's a story for another time far in the future. We're going to see this again, and we're going to use our local linearizations for some more tricks that I have not shown. Any final questions? Okay, I'll see you tomorrow.